Today, we're going to revisit a problem of perfect square with certain pattern. Here, I give an example of a big number. Notice that this is 11-digit number, and it's going to repeat itself. All right, so that's going to be the digits and concatenated with its own digits. It turns out this number, big number, 22 digits in total, is a perfect square. Now today we're going to find out how many perfect square of this particular pattern. Right? Let's do some analysis. Right? So first of all, the perfect square, just a review, it is an integer square. The smallest, of course, would be 1, which is 1 square, 4, 2 square, 3 square, 4 square, 16, 5 square, 25. Of course, the bigger numbers like 10,000, right? Or 100 million, and so on and so forth. So we're going to find out the perfect square in the form of a repeating numbers, right? As we mentioned earlier. Now, this is the example, right? We have an integer and repeats the digit, and it turns out to be a perfect square. Today, we try to find such numbers. Let's do some analysis. We claim that if we have integer x with n digits, then if you put x with its digits concatenation, the new integer is going to be 10 to the nth power plus 1 times x. Now, for example, let's say number x is 2023, which is a 4-digit number, right? n equal to 4. Then when you do this concatenation, you're going to have 2023 followed by 2023. This number can be rewritten in terms of 2023, which is x, as 10 to the first power plus 1, right? 1, 0, 0, 0, 1 times 2023. In other words, it is this. In general, if x is at nth digit, then x with concatenation of itself is going to be this new quantity here. So let's find out when would this be a perfect square. We make a few claims first. Now notice that since x is n-digit number, 10 to the nth power plus 1 is n plus 1 digit, even though it starts with 1, but it has one more digit. So we claim that this part is always greater, strictly greater that is, than x, because it has one more digit in the decimal representation. Alright, so that's useful property. And in order for the thing to be a perfect square for some integer m squared equal to this quantity here, we make another claim. We claim that 10 to the n plus 1 as an integer must contain p squared, at least p squared factor for some prime number p. So why that's important? Right. First of all, we want to prove this claim. Right? This can be proved by contradiction. Let's assume 10 to the nth power plus 1 would have prime factorization where every prime factor has degree of 1. There's no p squared in the factorization. Okay, let's assume that is the case. In other words, 10 to the nth plus 1 is going to be a bunch of distinct prime factor multiplied together. There's no powers here, right? If that is the case, in order for the whole thing to be a perfect square, then this x would have at least p1, p2, and pr in order for them to be a perfect square. So, which implies that x is going to be greater than this, because x must contain at least these prime factors, and among others. So which means the minimum value of x is already 10 to the n plus 1, which is a contradiction. Earlier we claimed x is n-digit integer, 10 to the n plus 1 is n plus 1 digits integer. So that's a contradiction right there, which means through the proof by contradiction, we know 10 to the n plus 1 must contain p squared for some prime number p. Now, why is that useful? Because, what is 10 to the n plus 1? It's a special number in terms of a different value of n. When n equal to 1 is 11. When n equal to 2 is 101. When n equal to 3 is 1001. And one bunch of zeros and 1. Alright? How do we factor that? So we're going to do some experiment. Let's n to be 1, 2, up to, let's say, 15, for example. Right? Let's try to do the prime factorization of those numbers. You can do it with pencil and paper, but here we're going to resort to a Python program for the factorization. I'm going to skip the Python code part. I'm just directly show the results. Okay, so for the 11 is a prime number. And then for 7 times 11 times 13, so we don't have a p-square. Now, in fact, the first square term or more is actually when n equal 11. Let's focus on that. All right, that's good. Because when n equal 1, 2, 3, up to 10, those are distinct prime factorization. And only when n equal to 11, where we have 11 squared as a prime factor, let's focus on that. That's the smallest n we can find. Right? So let's do some analysis. In order for this to be a perfect square, right? And x must be an 11th digit when n equals 11. So we already know that this factorization. So x, in order for the whole thing to be a perfect square, x must contain 23 as a factor, 4093, and 8779. So x must be in this format, and times r squared. Now notice that what is the product of this? If you do the multiplication, this turns out to be a 9-digit number. We want to find r such that x is a 11th digit, right? Because n equals 11th, right? So let's do that. Again, let's use Python to find out all the values from r equal 4 to 10, right? For the 11, that's already too much, right? And let's do the verification, right? So this is x, this is x concatenation with x, right? Just repeating the digits here. It turns out that all those numbers are perfect squares. So we have found 7 different 11-digit numbers, satisfy the desirable pattern, and they're all perfect squares. Today, through some mathematical analysis and some proofs, we concluded that we have found 7 distinct 11-digit perfect squares with the desirable pattern. Hope you enjoy the process. However, the journey doesn't end here. So the question is, can you find the next batch of perfect squares that follow this interesting pattern? Please do some exercise and share your answer in the comments below. Hope you enjoyed the video. Please like, share, and subscribe to the channel.